one-dimensional heat equation or diffusion equation. Di of Q is a diffusion equation. One-dimensional heat equation or one-dimensional diffusion. Before we enter into that one-dimensional diffusion equation, I listed one important point in Fourier series. It is called the Dirichlet's condition. Dirichlett first appears. Dirichlet's conditions. Dirichlet's conditions. Actually, this is a sufficient condition to expand any function as a Fourier series. So you can write that any function f of x can be developed as a Fourier series. Fourier series provided. You know what is a Fourier series? But the Fourier series is a naught by 2, the summation of n equal to 1 to infinity a in cos n x plus b n sin n x. Already we have discussed many problems on this. Okay, so provided some conditions are there. One, f of x is periodic. F of x is periodic. Single valued. And finite. F of x is periodic, single valued and finite. Second one is f of x has finite number of finite discontinuities. Finite number of finite discontinuities in any one period and as no infinite discontinuity. See, actually what is called that, you already explained about that periodic, that is single valued and finite. This can understand, but f of x has finite number of finite discontinuity in any one of the period and no infinite discontinuity. What is called that infinite discontinuity? If you take the tan x, for example, if you take tan x, so what is the tan x graph? Go to here and then discontinue here. Once again, it starts from here. So this is the tan graph. So for the tan x, we are not able to find the Fourier series. For the tan x, like tan x or cosecant x also. Cosecant x also having that infinite number of discontinuities. For these two functions, we are not able to write the Fourier series. Okay. Third one is f of x has at the most a finite number of maximum and the minimum. Okay. Actually, here what is called the most finite number of maxima and minima. In case f of x is a periodic function. If it is a periodic function, that should having that a maximum value and a minimum value. For example, sine and cos is a periodic function. It has a maximum value and a minimum value. Okay. Now we come to the problem, that is one-dimensional heat equation or one-dimensional diffusion equation. So what are the what is called that one-dimensional heat equation? One-dimensional heat equation. Dou u by dou t equal to alpha square dou square u by dou x square. Easily you can remain this formula because one-dimensional wave equation is dou square u by dou t square and alpha square dou square u by dou x square. That is one-dimensional wave equation. One-dimensional heat equation is dou e by dou t equal to alpha square dou square u by dou x square. Here, where we are going to find that one-dimensional heat equation. You consider one rod of length L. Already we have discussed one example to find that one-dimensional wave equation. For that one-dimensional wave equation, we have considered one string, a string of length L. Okay, but here we are considering one rod of length L. Just like it is end A, it is end B, end A and end B. In the rod, anywhere we are heating. Okay, from this side or this side. Okay, so here in case I am heating that point, and then it is the insulated rod. INSULATED. What is called means insulated rod. Okay, if you heat somewhere, in case if I heat somewhere, if I heat here, okay, immediately that heat is not captured by this rod. Okay, throughout this side, totally heat, then only the heat will be slowly move into that rod. Okay. Similarly, here also, if I heat here, then uniformly heat is distributing throughout the rod. Okay, that is called the insulated rod. Okay, fine. So if you are heating here, then slowly move to here. Then what is our aim? Our aim is to find that finding U. U is the temperature. U is the temperature of the rod. Then it is a function of x comma t. U is the function of x comma t. Otherwise, we can write directly u of x comma t. What is meant by u of x comma t? U of x comma t means temperature of the rod at any time t. At any time t at some distance x. At some distance x. Okay. So here how to find the solution of this one-dimensional heat equation. And then here, one-dimensional heat equation is dou u by dou t, that is equal to alpha square dou square u by dou x square. Where one important MCQ is there. What is alpha? Alpha square is a by rho. Actually, K is thermal conductivity. K is thermal conductivity. What's the name? K is thermal conductivity. Rho is density. Rho is density. C is the specific heat. K is the thermal conductivity. Rho is the density. C is the specific heat. So all them are that for the material. For the material to material, it will be vary. We are taking alpha square is constant, but based on that, the varies of K and rho and C, that alpha square will be vary. Okay. How to find the solution for one-dimensional heat equation? By variable separable method, first we will find that the solution of one-dimensional heat equation by variable separable method. The variable separable method. U is that x comma t. At x comma t, that can be written as x of x into t of t. X of x into t of t. So you can find the dou u by dou x is x dash t. Similarly, dou square u by dou x square is x double dash t. Next we have to find dou u by dou t is there, na? Dou u by dou t. When you are differentiate with respect to t, keep it that x as constant, t dash, okay, right. So substitute all the values here, we'll get that x double dash x t dash equal to alpha square x double dash t. Okay, x t dash equal to alpha square x double dash t. Next we can write that you cross multiply here, x double dash x is the cross multiply that x double dash by x equal to x double dash by x equal to alpha square t dash by t, equating to some constant k. Equating to some constant k. The next step, you can write that x double dash by x equal to k 1 by alpha square t dash by t equal to k. So x double dash minus kx equal to 0, t dash minus k alpha square t equal to 0. So here we can write This is equation number 1. This is equation number 2. Equation number 3. Equation number 4. Okay. So here K is there. K is, there are 3 cases are there. Already we have discussed in the one-dimensional wave equation of K is positive, or K is negative, or K equal to 0. So take it the case 1. Case 1. K is positive. If K is positive, that means take it the K equal to P square. K equal to P square. Then 3 and 4 can be written as x double dash minus P square x equal to 0. So here also we can write P dash minus K. K is P square, P square alpha square P equal to 0. Now you solving that, x double dash minus P square x equal to 0. Na? So we can write that x double auxiliary equation is m square minus P square equal to 0. M equal to plus or minus P. So what is x value here? X is a1 e power px plus a2 e power minus px. Similarly, for the second one, m minus p square alpha square equal to 0. So m equal to p square alpha square. Therefore, we can write that t equal to a3 e power p square alpha square t. But we know that u is u of x comma t. Here we are writing that u of x comma t is x of x t of t. So we are finding here x of x and t of t. We can write that u of x comma t equal to u of x comma t equal to a1 e power px plus a2 e power minus px into a3 e power p square alpha square t. So okay, this is one equation. This is one equation. Second case, case 2. Case 2. In case K is negative. K is negative. That means K equal to minus P square. Therefore, the 3 and 4 becomes x double dash plus P square x equal to 0. P dash plus alpha square P square P. So what is the auxiliary equation here? M square plus P square equal to 0. M equal to plus or minus IP. Therefore, what is x here? X is A4 cos px plus A5 sin px. Because here roots are real and complex. Already we have solved that one-dimensional, ordinary differential equation in this first semester. Already we have discussed it. So I don't want to repeat the same thing. How to write the complementary function, how to write the particular integral. Already you know that. So here m equal to m plus alpha square p square equal to 0. So m equal to, or this one, m equal to minus alpha square p square. So what is c here? C equal to a6, a6, sorry, here I can write C equal to a6, C equal to a6 e power minus alpha square t. But what is u of x comma t? U of x comma t is x of x is e of t. So what is x of x here? A for cos px, a for sin px, a for cos px plus a for sin px into a6 e power minus alpha square p square t. Okay, second equation. Then final one is in case k equal to, so in case k equal to 0, we could put x double dash equal to 0 and then t dash equal to 0. So what is x here? X is a7x plus a8. C is some constant a9. So finally you can write that u of x comma t equal to a7x plus a8 equal to a9. Sorry, now to multiply not into t. Into a9. So what are the possible solutions here? There are three possible solutions are there. This is first possible solution. U of x comma t equal to a1 e power px plus a2 e power minus px, a3 e power p square alpha square t. Second one is a4 cos px, a5 sin px, a6 e power minus alpha square p square t. And then u of x comma t equal to a7x plus a8 plus a9. So what is the suitable solution? What is the suitable solution? How to choose the suitable solution for that one-dimensional heat equation out of these three possible solutions? Okay. Now listen. U of x comma t, then that should be the function of t. Actually, here you can see there is no function of t here. T is missing. T is missing. Therefore, this is not the suitable solution. And one more thing here. In case if we heat the rod and then we stop to heating the rod, we stop to heating the rod. The first law of thermodynamics is that this is a very basic one. First law of thermodynamics. Law of thermodynamics. What is called as the first law of thermodynamics? If time t is increasing, the heat in the rod will be decreasing. If time t is increasing, the heat in the rod will be decreasing. That is the first law of thermodynamics. First law of thermodynamics. If you are heating the rod, okay, then after some times you are calculating time t. Then you start the time t after some time. So at the time when time t is increasing, so if you stop the heating the rod, what happens? The temperature U will be decreased. Okay. So here we can see that if time t is increasing, see that the temperature also increasing. The temperature also increasing. So this is also the not possible solution. Come to the third solution. The third solution, if time t is increasing, it is, you can see that e power minus is there. E power minus is there. What happens? If time t is increasing, the temperature will be decreasing. The temperature will be decreasing. Therefore, the solution number 2 satisfying the condition. Solution 2 satisfying the first law of thermodynamics. First law of thermodynamics. First law of thermodynamics. Therefore, the solution of one-dimensional heat equation. The solution of one-dimensional heat equation. U of x comma t equal to. So how can we write that? So here A4, A5, A6 this we can generalize that. If we multiply that A6 inside A4 into A6, we can write that A5 and A6 we can write that as B. So we can write that. Otherwise, constant 1, constant 2. You can write like that. Okay. So either you can write C1, C2 or A and B. So A cos Px plus B sin Px. A cos Px and B sin Px e power minus alpha square B square T. Is a suitable solution for one-dimensional heat equation. Now we will see that some problems. Okay. Type that. Problem number 1. The rod of length L. The rod of length L with insulated side is initially at a uniform temperature. Yeah, uniform temperature f of x, uniform temperature, f of x. If n's are suddenly cooled to 0 degrees C and are kept there and at the temperature at the temperature at the temperature. Find the temperature function. Find the temperature function of u of x comma t at any distance x, any distance x at any time t. Okay. So here we can write the solution for this. First we have to write that a rod of length L, if the function is, if the problem is given a rod of length L, we have to use the one-dimensional heat equation. Otherwise, a string problem is given, we have to use the one-dimensional wave equation. So here we can write the solution. The one-dimensional heat equation is dou U by dou T equal to alpha square rho square with the. So what is the solution here? The suitable solution. Solution of one is u of x comma t equal to a cos x plus b sin x e power minus r square is number 2. Next, for the given problem, we have to write the condition, initial condition. So what are the, first we have to write the boundary condition. Boundary condition. What are the boundaries here? Okay, consider one rod of length L is given, a rod of length L. Two ends are there as an insulated sides. Two ends are there, A and B. If ends are suddenly equal to 0 degrees C, so here they are keep the 0 degrees C and then 0 degrees C. If the rod of length L, then we can take it this as in case x equal to 0. In case we are taking x equal to 0, this we can write that x equal to L. Therefore, the boundary conditions are, first boundary condition, u of 0 comma t equal to 0 at t is greater than 0. At any time t, always we have to keep it that both the ends are at 0 degrees. U of L comma t also equal to 0. The last one boundary condition is there. Initially, at uniform temperature function is f of x. That means initial means u of x comma 0. That boundary condition, u of x comma 0 is some function f of x. This is the initial condition. See, only one difference is there between that one-dimensional wave equation and one-dimensional heat equation. For the one-dimensional wave equation, two boundary conditions are occurred, two initial conditions are occurred. Okay. At the same time, for that one-dimensional heat equation, two boundary conditions occurred, one initial condition. One initial condition required for to solve that one-dimensional heat equation. So apply initial condition 1. First you have to apply the zero boundary condition, then you apply the non-zero boundary. Apply that initial condition, not initial condition, boundary condition 1 in 2. What is the first boundary condition? U of 0, t. What is meant by u of 0, t? Substituting x equal to 0 here. If you are substituting x equal to 0, what happens? This value is 1, this value is 0. So a into e power minus alpha square p square t. But u of 0, t is 0. A into e power minus alpha square p square t. But here, that e power minus alpha square p square t equal to 0, what happens? If e power minus alpha square p square t is 0, then u of x, t will be fully 0. So, this is not equal to 0. E power minus alpha square p square t is not equal to 0. Okay, so only possible is, therefore, a equal to 0. Substituting a equal to 0 in 2. What happens? In case if you are substituting a equal to 0 in 2, we'll get that this term will be 0. Then only this term will come. So u of x, t is u of x, t equal to b sin x e power minus alpha square t. Okay. Equation number 3. This equation number 3. Next, you have to apply the boundary condition. What is boundary condition to u of L, t? U of L, t. That is also equal to 0. But what means that u of L, t? U of L, t means you have to substitute x equal to L here. So b sin L into e power minus alpha square p square. Already we know that e power minus alpha square p square t is not equal to 0. In case b equal to 0, then u of x, t will be 0. Therefore, p is not equal to 0. Only possible is sin PL equal to 0. So we can equate that. We know that WKT means we know that sin n pi equal to 0. So instead of 0, we can write that sin PL equal to sin n pi. Therefore, P equal to n pi by L. So, substituting P equal to n pi by L in 3. P equal to n pi by L in 3. Then, substituting the P equal to n pi by L, you can get that u of x, t equal to u of x, t equal to b sin n pi x by L into e power minus alpha square n square pi square p by L square. This is equation number 4. But before applying that, non-zero boundary condition, generalizing the solution. generalizing the solution. How to generalize? Taking that B equal to summation of n equal to 1 to infinity Vn. Then U of x comma t equal to summation of n equal to 1 to infinity Vn sin n by x by l into e power minus alpha square l square t by l square. Now finally we have to apply the last boundary condition. Sorry, initial condition. What is the initial condition? Initial condition is u of x comma 0 equal to f of x. U of x comma 0 means keep it x as it is, but you have to substituting t equal to 0. Applying the initial condition u of x comma 0 equal to some f of x. So what is u of x comma 0? U of x comma 0 equal to summation of n equal to 1 to infinity Vn sin n by x by l into e power 0. But you know that e power 0 is 1. So, but u of x comma 0, what is u of x comma 0? U of x comma 0 is f of x. No? F of x equal to f of x equal to summation of n equal to 1 to infinity Bn sin n by x by l. You know this is the half range Fourier sine series. Half range Fourier sine. Half range Fourier sine series. So you can find that Bn, you can substitute that Bn there, then we can get it. So Bn equal to, what is Bn formula? 2 by n integral over 0 to the f of x sin by x by l into d. Is it not? So therefore, what is the solution? The solution is u of x comma t equal to u of x comma t equal to, this is the solution, summation of n equal to 1 to infinity, summation of n equal to 1 to infinity, rho by n, integral over 0 to the f of x sin by x by l into dx into this Pn, sin n by x by l into sin n by x by l into e power minus alpha square n square I square t by l square. Right? Solution of the problem. Okay. For example, you can take one problem. Solve dou u by dou t equal to alpha square rho square over rho x square subject to the condition. Subject to the condition u1 u of 0 comma t equal to 0 for t greater than or equal to 0. Second one, u of t comma t equal to 0 for all t greater than or equal to 0. Last, third one is u of comma 0 equal to x. 0 less than x less than L by 2, L minus x, L by 2 less than x less than or equal to L. Okay. So how to solve this? Here, these two conditions are boundary conditions. This condition is the initial condition. Okay. So we have to solve the problem. The solution of one-dimensional Pt equations u of comma t into a cos px plus p sin px into e power minus alpha square is square. Okay. So applying that initial condition 1. No, I don't want to repeat. A equal to 0. Apply the initial condition 2. We get that P equal to n pi by L. So next only one initial condition is pending. After applying that boundary condition 1 and 2, what is the solution here? After applying the boundary condition 3, after applying that means initial condition. Before applying that, before applying the initial condition, this is the solution. U of x comma t equal to the solution becomes u of x comma t equal to summation of n equal to 1 to into Pn sin pi x by L into e power minus alpha square into L square. Okay. Now apply the initial condition 1. So now to apply the initial condition. Okay. Initial condition u of x comma 0 that is equal to summation of n equal to Pn sin n pi x by L. But u of x comma 0 is what? U of x comma 0 is x L minus x. X is 0 to L by 2, L minus x is L by 2 to x. So, sorry, L by 2 to L. Let's how to find that value. That means u of x comma 0, no? So f of x. It is the function of x equal to summation of n equal to 1 to infinity Pn sin n pi x by L, where Pn equal to n by L several over 0 to L f of x sin n pi x by L dx. But here f of x is what? Bn equal to 2 by L integral over, we have to split it. 0 to L by 2 f of x. F of x is x sin 1 to x by L dx plus remaining L by 2 to L. Here f of x is L minus x. Okay. Solve this by using the Bernoulli's formula. Solve this by using the Bernoulli's formula. We will get that Bn equal to, so expand this 2 by L. Keep it that x here. Integration of sin is minus cos x by L divided by n pi by L minus differentiation of x is 1. Integration of minus cos minus sin. So what is the interval here? 0 to L by 2 plus 2 by L 2 by L minus x L minus x minus cos n pi x by L divided by n pi by L minus L minus x. Differentiation is minus 1. Integration of minus cos is minus sin n pi x by L divided by n pi by L whole square. But here the interval is L by 2 to L. So applying that L by 2 here, we will get the cos n pi by 2. Applying that 0, what happened? Everything is 0. Both of them are 0. So here also we can substitute that L here. We will get that 0 here and then 0 here because sin n pi is 0. So we have to apply only that upper limit here. We have to apply that lower limit here. That means L by 2 and L by 2. Then if you are applying the upper limit and lower limit, what happens? 2 by L. Next step you can write the 2 by L minus x L by n pi cos this is not there. No? We have to substitute that L value. So L square by 2 by L 2 n pi cos n pi by 2 cos n pi by 2 plus L square by L square pi square sin n pi by 2 plus L square by 2 n pi square by 2 n pi cos n pi by 2. But it is not there. So don't do. Plus L square by n square pi square sin n pi by 2. So here that this get cancelled. Remaining is Bn equal to 4L by L square pi square sin n pi by 2. So substituting that Bn in that equation, here we have to substitute that Bn here. Substitute that Bn here. We will get that u of x comma t equal to u of x comma t equal to 4L by pi square additional n equal to 1 to infinity 1 by n square sin n pi by 2 into sin 1 x by L into e power minus alpha square x square y square t divided by this is the answer for this. M Divya. So, yeah, M Google Drive. Okay.